Lagrange multiplier. Now this equation, I'll write it in a slightly different way. And now the rest of it is just thing, a plus lambda gradient of G is equal to 0. Can I just rewrite it like this? Right. And now with both with this, from this we can conclude that gradient of E plus lambda G is equal to 0. So what are we trying to do? So we are trying to minimize, let me just call it L, right? You're trying to minimize not just the total error, but another function, loss. It's called the word loss. And thus we get introduced to the big concept of loss in machine learning, the loss function. L is your loss function. What you're doing is you're minimizing not E, but the sum total of E plus lambda G. Are we together? Right? So hold your thoughts, guys. Let me tell you some of the consequences. And so these two have opposite effects. If you minimize just only E, you'll go far from the origin. Then what will happen to G? You will have to have a pretty large constraint surface going all the way out to that point, isn't it? So G will increase. So if you try to minimize E only, then your solutions that you'll get will be at large G. You don't want that. So they have opposite effects. So you have to be careful. You want to keep G small and you want to keep E small. And you have to bring them both down while both are competing. They're pushing each other out, right? That is the constraint optimization. Now, let me write it down, this loss. Once you understand, so now if you realize what I did is I use this problem of machine learning, loss surface, and error surface and constraints to introduce you to actually a powerful idea of constraint optimization in calculus. So once you understand this idea, for the rest of all the discussions that we'll do in machine learning class, I'll assume that you understand constraint optimization, right? Because we'll reuse this idea at many, many places. Here, we will write loss is equal to E plus lambda G, right? Then in the case of regression, remember what this is, or let me just say regression. In the case of regression, this is what? E is the sum squared error, yi minus yi hat squared, isn't it? You can take sum squared error, you can take mean squared error, it doesn't matter. You can take this, or you can take 1 over n, doesn't matter. Am I together, guys? It is the same thing. Error is error, right? You may or may not take this. So I will skip this. I will just skip this quantity plus lambda. Now, what was G? Remember, the G was not in the real space. G was actually in the beta space. It was beta naught square plus beta 1 square, because where was the circle being made? In the hypothesis space. Do you see this, guys? This is the hypothesis space. In the hypothesis space, equation is in terms of betas, right? So this is true. Let's bring it here. So this is equal to beta naught square plus beta 1 square, right? So people often write this equation as square plus lambda summation of beta j square, right? J being the number of parameters, j is equal to 1, and suppose the model has p parameters, right? Whereas this I is equal to n, number of data points. This summation is over a data set. This summation over parameters of the model. And this is therefore the celebrated equation of the famous equation of L2 regularization, or ridge. It is called regularization, or most often when people say they're regularizing, this is by default the regularization that people use, right? This is the famous equation, right? You must remember this, and your book will talk about. Now, what happens is most of the books, in fact, don't explain how you arrive at this. They just give you this equation as a fact that regularization is to minimize this loss equation. And if you do this, then you won't have oscillations. Your parameters won't become large. They don't actually I mean, sometimes they do, but most of the times the books that I've seen, they don't tend to explain. So I have taken you through an intellectual journey in which we have tried to understand how this equation, excuse me, I apologize. I need water, guys, so we'll take a break after this. Yeah.
So Asif, one quick question I have. So equation that you have beta j, where j equal to 1 to p. But the one that you have is a beta 0 to beta 1 plus beta 2. So intercept is not the part of that?
Sorry, let me make it 0. Better. Good. So they are a p plus 1. You're right. Like, that is good. So what it does is we have this famous equation now of, and we went through the intellectual journey of understanding it. I will just recap this journey and then we'll take a break. So this journey basically says that, see, if you do unregularized, or now the word ordinary, you must have seen this word in literature. The regression, linear regression that we learned is called OLS, ordinary least squares regression. Why ordinary least square regression? Because the loss function is the same as the error function, the sum squared error function. It does not contain the other term. When you do put the other term, it is regularized regression. So what we were doing till now was ordinary least square regression, namely unregularized regression. Are we together? Right. This is an important point, and we have gone through the journey. It's a very simple journey. It basically says, hey, if you are not careful, your parameters will blow up. How do you prevent it from blowing up? You put a circle around the origin and say, no matter what, I'm not going to go out of it. The learning must tell me the best value, the minimum error point within my circle. So which of these points that I have within my little disk here, a sphere here, which of these has the least error? And whatever that answer is, I'll consider the right answer, not the absolute sum squared error minima, the bottom of the error surface both. So you change the loss function itself, and this is where you stop, right? So with that thought, let us now take a little break for about 10 minutes. All right, so we realized two new concepts. First is our error function is not just the sum squared error term or mean squared error. If you want to average it out, doesn't matter. I'll just stay with sum squared. It's not that. It is that augmented with a constraint term, right? A budget term. You have to choose how far you're willing to go from the origin. And based on that, you have a budget. Actually, the how far is well captured by this parameter. That is why it is often called the regularization hyperparameter. Why hyperparameter? Why do we think it's an hyperparameter? It is not something that machine learning will tell you during the learning process. You set a budget and it will tell you that for this budget, this is the best we can do, isn't it? This is the best model we can build. But you have to now move back and forth, slide the lambda value, decide how big or small your circle is or your sphere is to find which one gives you the least test error, right? So that comes through hyperparameter optimization. Now, since we are encountering these hyperparameters n and now lambda and so forth, it raises. So if you're doing polynomial regression, you realize that we already have two hyperparameters in our model. What is the value of n, the degree of the polynomial, and what is the lambda, right? And so life is getting complicated. We have to search in 2 dimensions. What is the best of that, right? And so that brings us to the very, very interesting field. How do you find the best value for all these hyperparameters, right? Because for each combination of hyperparameter n and lambda, you have to do one more machine learning exercise. You have to train the model all over again, and there are infinitely many values. So how will you find the best? That topic is a very interesting topic. It has some very simple ideas like grid search, randomized search, etc. But actually, it has become a full subject with very interesting ideas. The field is literally called hyperparameter optimization. And we use Bayesian inference methods to do it, Bayesian optimization to do it. It is a topic that I intend to take you at some point in this workshop, time permitting. In this workshop, we are, depending upon how fast we can move, I don't know whether I will or will not, but we'll certainly cover it in depth in the next workshop, the follow-up workshop, because there it becomes a big topic. So now, let me summarize what we have learned. In the parameter space, beta naught, beta 1 space, you draw a circle. This is, you tell your circle is determined by your lambda or whatever. Then what you do is, you have the absolute beta star is somewhere here. And so you have this and you pick this point as your real beta. This is the constrained optima, constraint optima or constrained minima. Are we together? Because at this point, the grad G and the grad E will be opposites to each other. That is what we learned. But then comes a very interesting question. What is a circle? We always assume the equation of a circle is x, beta naught square plus beta 1 square is equal to some constant, the radius square. But now I'm going to shake that value and generalize that concept. Let me define. So we will talk about Minkowski norms. Minkowski was, again, a great mathematician. And this term is associated with him. He asked this question. Let us define a circle. So circle is something that we always think of as round, but he took a different definition. He said, suppose we define the circle to be the set of all points fixed distance d from the center, right? For simplicity, let's take the center to be the origin. Let's say we situate the center at the origin. So ponder over it. What does this agree with your intuition of a circle? It is the set of all points which are at the same distance from the center, right? We would say that. Now, innocent looking as it is actually, Minkowski just made a tremendous generalization on the concept of a circle. And let me explain that to you. If you are a taxi driver, and typically it is one of the first cities that was built on a grid was Manhattan, isn't it? Manhattan, the city, was laid on a grid. So let's say this is Manhattan. I'll take this, Manhattan. Manhattan city. Grid. Streets. Do they look like this? Isn't it? Let us say that you are a taxi driver. Well, these days, taxi drivers are becoming an extinct species. So let's say one of these Uber, Lyft, and whatnot drivers, right? We'll use the word taxi driver as generic for all of them. You are at a point, let's say that you are at this point, right? At this point, I tell you that you have enough gas to go, let us say only 1 mile. Are we together? You have, or maybe 1 mile is too little. No taxi driver will drive when he has only 1 mile's worth of gas. Let's say he can drive 10 miles, right? Or she can drive 10 miles. So what can the taxi driver do? Let's say that at 10, each of these grids are how many? Okay, we'll just say that this is 1, 2, 3, and let me bring one more green one, 4. This is 10 miles. Let us say that, that this is a point from, this is the origin. This is where he starts with and could go this distance. Now this gentleman could have gone, or this taxi driver could have gone 10 miles in the opposite direction. 1, 2, 3. Oh, I need one more green light. Could have gone here instead. That is also 10 miles away. Would you agree? Likewise, 1, 2, 3. I just seem to have missed one more line everywhere. And 1, 2, 3, 4 here also. So you can go 1 mile here, 1, 2, 3, 4, or 1 mile here. You could go in any direction, 1 mile. Well, 1 mile or 10 mile, whatever. I'll just call it 1 mile. Sorry. Or you could have done this. The person could have gone 3/4 mile here and then gone to this point. Would you agree that this is also the same distance from the origin? Driving distance, not distance, driving distance. Not as the bird flies, but as the taxi drives. And the same is true for this point. You could have gone like this, right? Or you could have gone like this, right? Isn't it? And like that, this, these, this, they are all the same. They are all the same distance. You could have gone in many other ways. You could have gone like this, right? You could have gone like this. So you can pick your path. But no matter which path, so long as you're not plowing your way through buildings, right? The taxi would go like this. All of these points, as far as the taxi is concerned, they are equidistant. So I'll say the statement: for the taxi driver, all the circled points are at the same distance from the origin. Would you agree with that? So what happens if you connect these dots, and assuming the taxi driver can only drive parallel or perpendicular, like has to drive Oh, sorry. What did I just now do? I did something. Sorry. Yes. So long as you only go parallel to the axes. You cannot go in any direction except parallel to one of the axes. Would you agree that this rhombus shaped, this diamond shaped thing that you are seeing fulfills the definition of a circle? Do you see that? Right? It fulfills the definition of a circle. What this distance is, because here the distance is defined as the amount that you go, whatever. So suppose you take any point x, y. It means that you have gone x horizontally and y vertically. Yeah. X plus y. Would you agree that this is our definition of, convince yourself that this is a definition of distance? It doesn't matter positive direction, negative direction, along the x-axis, however, whatever distance you have got, magnitude. So magnitude of x. Likewise, after that, how much up, down you have gone, right? Doesn't matter whether you went up or you went down, but it is the absolute magnitude. So this is the definition. So we call it the Manhattan definition of distance. And this is very interesting because we realized that if you use a Manhattan to the taxi driver, a circle is diamond look, has this rhombus like look. You agree, guys? It has this peculiar look, or it's a square actually on its side. It's a square look. It doesn't look the round curve that we have in mind. And so
ask if so we are twisting the definition of the circle itself this way, right? Like we are looking at the circle from a straight line from one place to the other. Here we are bending all this, so we can have infinite number of turns left and right.
yes,
We can do the same thing.
exactly. So for example, you could go like this, and still end here. Do you notice that?
Yeah.
But in Manhattan, of course, it wouldn't be infinite. But if there were no buildings in between, and assume that you are allowed to go only parallel or perpendicular, then there'll be infinite number of paths from one point to another. Still, right?
Yeah. But my confusion is, how are you equating this to a circle?
No,
yes, this is one equidistance. I understand that, but the definition of circle is entirely different from this, though.
Exactly. So I'm defining circle as this. So now I'm saying circle is not that round thing you're used to. Minkowski said, well, let us redefine circle, a more general definition of a circle. Circle is the set of all points that are at the same distance from the center.
But here, if you take a left and right, you may not be on that rhombus. It will be somewhere in between. Right?
No. You still have to go one whole mile.
Yeah, but if I go up, left, right,
Now convince yourself that if you must go 1 mile. So what happens? See, think about it this way. I can go 2 steps like this and 2 steps up.
Okay.
So then I ended up here. I can go 3 steps like this and 1 step up. I end up here. Or I could go 1 step like this and three step up. I'll go. So what are you ending? You're ending up, whichever way you look at it, you're ending up with point.
You expect the direction that one right, one left.
No, I'm saying you can only go parallel to the axis. That's all. You can only drive on the streets.
Even multiple left also to the
Yeah. So for example, look at this. I go here, 1 right, 1 up.
and then you can take a left.
Oh, no, you don't. You want to find the shortest path to that point. So I should enter that word, shortest path. Yeah. You need to have the shortest path that you can take, because taxi drivers don't want to take long path unless well, actually they do. They have meters. They want the meter to run, but an honest taxi driver takes the shortest path, right? So this is it. The shortest path from the origin to any one point will be on the rhombus.
Right.
Also, we'll be on that square. Well, of course, like that.
You can get from the origin is basically
that, yeah, because you have to go 1 mile, right? And you have to take the shortest path there. So this is how you'll do it, isn't it?
But
So here
Asif, in the Go ahead.
So here you've divided 1 mile into 4 parts. So if we divide it into say 50 parts, then slowly becomes a circle, is it?
No, 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 it does not. Let us do that. Suppose that, so I'll make another grid just for the sake of this argument. And you can now take the asymptotic limit. Suppose I have this axis, this axis. Now I'm removing the streets, but I'm just keeping the constraint that you can only drive along one of the axes, right? So suppose you have to reach any point here. What will you do? Suppose the coordinates of these points are, actually, I need to brighten it up a little bit. Let me take a color. Which color? Okay, the same color, but a little bit bolder. So suppose this is a point. So the simplest path you can take is you can go X distance and you can go Y distance up. Would you agree? Doesn't matter. Now I've removed the grid, so it doesn't have to be in steps of 1, 2, 3, 4, whatever arbitrary distance, some 2.5. Let's say that it is 0.3 miles in X axis and 0.7 miles on the Y axis, right? To go here. So what is the shortest distance? This is the shortest distance to XY, right? And that distance is, of course, more than going as the bird flies. The bird flies is different, right? You're doing as the taxi drives. So definition. So the interesting thing is, this is the game mathematicians always play. See, great ideas are born from simple concepts, down to earth concepts that we are all familiar with, but putting a little generalization on top of it, generalizing it to in a way that now you can have different, more interesting definitions of a circle. So if we define a circle to be the set of all points of fixed distance from D, now the only question is that how are you allowed to move, isn't it? Can you do as the bird flies, or must you do it as a taxi driver? Do you see that? This definition is as the bird flies. The normal circle is as the bird flies. So let me summarize what we just said. For circle, for Manhattan distance, taxi driver, and literally these are the words used in mathematics. In literature, in machine learning books, you'll find these words being used. Distance is X plus Y, the absolute value of the displacements. Isn't it? X displacement, Y displacement along X and Y. And it is basically, just to summarize, is this: for Euclidean distance, which is the distance that we all are familiar with, distance, right, as the bird flies, right? Then what happens? As the bird flies, this thing has, 1 second, let me put the constraint here. Yeah, so as the bird flies, it is a circle from the origin. It is a circle, and the distance is X square plus Y square square root. Would you agree these two definitions by now? So it takes a little bit of time to get familiar with this distance notation. Are we together? And yes, go ahead, Sona. Come again? Yeah, from here, distance from here, right? Distance from here. And from the center, right? So distance from the center, or the origin, or whatever that you say, center. Or the starting point. Right? So wherever you start from, that becomes your center to measure distance from. You agree? So out of this, Minkowski then generalized this even further, and he said that the distance between 2 points, the nth norm, dn, he defined as something very interesting. He said it is x to the power n plus y to the power n to the square root, the nth root of that. This is the Minkowski generalized definition. N is the norm. Norm means your way of defining distance. Now, with this equation in mind, and this is the one thing I'll keep, we are very close to a very beautiful result actually here. For n is equal to 1, what does it become? d1 xy is equal to, let's look at this, x to the power 1 plus y to the power 1, the whole thing to the 1 over 1. And that is basically x plus y. What am I looking at? d1. d1 is what? Is basically Manhattan distance. It's Manhattan distance. Now let's look at d2. x2, right, is equal to x square plus y square to the power 1 over 2. Is this the same as square root x square plus y square? Because square anyway makes it positive. And what is this? Distance. And so now you realize that you have something beautiful. You can do d3, d4. You can keep generalizing it all the way to d infinity. Isn't it? Do you see this, guys? We now have the ability to come up with all sorts of distance notions. And we'll see the geometry of it in a little bit. This is your distance. So now let's see what does it look like. By the way, special case, what does d infinity look like? D infinity will do x to the power infinity plus y to the power infinity, right? I mean, some number very large, very large. So if you compare two numbers to very, very high powers, what will happen? The bigger number will dominate and the other number will disappear, isn't it? So max, what will happen is, and then you take the 1 over infinity of it. This is the same as approximately the maximal value, maximum of x or y, isn't it? It is basically the max of xy.
So after this max of x y will only on, suppose y is bigger.
Y is bigger. So basically what it means is that, yeah. No, so now I'll tell you the geometry of it. I'm coming to that, exactly that question. Huh? So hold that thought in mind. Now d infinity in practice you don't do, it's just a thought experiment. Huh? It's just a thought experiment. So how does it all look? So let's draw our coordinate system and I'll really draw it big. I hope it shows up huge in the screen. There we go. Even bigger. Kaya, let me know if it is visible from there on the screen coming through properly.
Yes, sure.
So a circle, oh my goodness, I'm so terrible at drawing circles. Well, if you squint a little bit, this thing will look perfectly round to you.
OneNote has shapes. You can use them too.
Come again? Oh, it has shapes. Oh, yes, yes, yes. The very good idea. Thank you for telling me that. Shapes. Circle. And how do I do the circle now?
Control and then drag, I think.
Control and
That's okay.
Which,
Actually, notice that. Like it did.
Did I? Well, okay, I didn't get a circle, but we'll take this lemon to look like a circle, right? This is a circle. So this is D is equal to, what is this D norm? D2 X, Y, right? Now, what is our Manhattan shape? Kind of like
Diamond.
the diamond shaped thing is this. So this is our D1 XY. Now what happens is that you go to a D, let's say D half, right? Nothing prevents you from doing that. Remember, nothing says that it has to be integer values. So that will begin to look like, oh no, this is too close to the other one. Let me take another color. Now, what color would be different from all of these? Maybe this guy. Do you see this? And if you take a number bigger, so this is D a half, right? XY. This is funny definition of distance. And if you take a number bigger than 2, let's take, well, I need one more color. I'll try this. If you take a number bigger than 2, it will be like, well, forgive my terrible drawing. It just has more bulge, right? You have a question in your mind, Kyle. Yeah, so what happens is that the more you take a bigger norm, the more it sort of swells out, right? So that gradually what it will become is, in the asymptotic limit, gradually it begins to go this. Well, just shows how terrible a drawing I have made, but this is your asymptotic limit. As you go more and more and more, it begins to head towards that, the square. So you can say that you, for very big values of norms, your notion of distance begins to look like the square itself, right? Yes, it's a very beautiful intuition. And this is the beauty of mathematics. Come again?
If the distance is 0, goes back to the
If not the distance, you mean the norm is 0.
The norm is 0, yeah.
Yeah, so I will let you think, go asymptotically, right? More and more pointy. It becomes more and more pointy. Yeah, yeah. So it becomes more. So what happens is that, so here's the constraint, confusion I'll give you. The bigger norms are more convex, they're bulging out a little bit till they'll begin to look like a square. The smaller norms, do you notice something? That small, anything less than 2 has pointy edges. It has these swords, this, the tip of the spear with the green and the blue. Do you notice that they have the tip of the spear on the axis, on the XY axis? This, it turns out, so now this is all a lovely mathematical exercise. How does it relate to our problem? Oh, we had a circle, we had a sphere as a constrained surface, right? We defined a circle to be a sphere. We can go and replace it with any one of these Minkowski norms now. Do you agree? Guys, remote, do you see that? We were limiting ourselves to a circle, but says who? We can go and put any one of the Minkowski norms. Let's use the Manhattan distance for a circle. Can we? So what happens is that, what
is the advantage of it?
Oh, we'll see that immediately. That's the point we're getting to. The advantage and disadvantage, there are both advantages and disadvantages of each norm. So for example, when we take this constrained surface that is like this, let's say this, and we have, let me just let me think of a constrained surface that will be very useful for us. let me see if this does our value. Sorry, not this. I shouldn't make this. I'm trying my best to cheat to make a point. So let us say that this constraint surface is, actually I should make my circles red. Let this be red. Once again, I take, so this is what we are familiar with, right? And let's say that my error surfaces are all like this. So where do I achieve the minima if I use the red circle? Here, somewhere here. This is my minima, isn't it? This is the beta naught axis and this is the beta 1 axis. And these are my error contour surfaces, circle of constraint. By now, this picture should have become very familiar to you guys. Is this true? Would you like this? Am I doing anything unusual here?
It's in the book, right?
Cheated a little bit. I've
SLR.
deliberately made sure that the point of contact is not on the axis, right? On the other hand, observe something very interesting. If I made it more pointy, if it was like this, the blue one, do you realize that there is almost no escaping the fact that the blue one will go and hit it here on the axis, isn't it? For the diamond, for the blue, for the Manhattan distance, the optimal point happens to fall on the axis, x-axis, isn't it? For the L2 norm, it happens to be somewhere else. Is this obvious, guys, from this picture?
Yes.
Right. So it turns out that here, obviously, I had to, I'm not very good at drawing, but this is actually true, even though I fudged here, it's almost always true. What happens is when you use in your equation, now go back to your loss function. The loss function with respect to the beta is defined as the y minus yi hat residual squared, the sum squared error term, plus lambda beta, right? Beta j. By the way, now can I write the beta j squared? J squared, j is equal to 0 to p. Right, and so I can write this also as I is equal to 1 to n, the sum squared error term yi minus yi hat square plus lambda. Do you guys realize that this is nothing but the dot product of beta with itself? Right. So let me write it in simpler notation. When I use this, and I'm doing, this is called the ridge regularization, as we in a little while ago we learned. Now, for when we use not the, this is the L2 norm, right? Remember, this is the Minkowski norm 2, but if we replace it with now, replacing with L1 norm, which is the blue line, a blue circle, well, in quote circle, because it doesn't agree with the notion of a circle. Lasso, it's called Lasso regularization. Either
beta naught or beta 1, but not both.
Yeah. So hang on. So this now becomes, the first term remains the same, right? I is equal to 1 to the number of data points, yi minus I hat square. But what does it do to the second term? The equation of the constraint is absolute value. That is right. This is j to p beta j, the absolute value, this equation, right? So this is Lasso regularization. And from this, you can imagine that you can create all sorts of more regularizations. isn't it? Just keep changing your norm and you will get. Now L1 and N2 are by far the most important. Now notice some observations. Observation. L2 tends to produce non-zero values for all the betas, right? Parameters. Would you agree? Like, look at the red dot. This is your red point. At this red point, is any of the either beta naught or beta 1 0? No, right? Isn't it? Are we together, guys? At the red point, neither beta naught nor beta 1 is 0, right?
Yes.
That is clear. On the other hand, L2, L1 regularization often, but not always, tends to hit the optimal point on one or more of the axis. Or more part you can ignore, or more part, because that now we are talking a higher dimensional geometry. But let's think of one. Here it happens to have hit on the x-axis. Why? Because all the pointy tips are on the axes, isn't it?
Or it could be where the line becomes a tangent.
Yeah, it could be. But quite often what happens is that, so that's why I said not always, but often, because you have pointy tips at the axis, you have these pointy tips. It tends to puncture or hit the error contour surfaces, often along the axes. Because it does that, because of that,
I have a question here actually.
one second, hold that thought. Because of that, some of the parameters vanish, right? Some beta j is equal to 0. So here, which particular beta j is equal to 0? If you look at this example,
Beta 1.
Beta 1.
yeah, right here.
Beta 1 is 0.
0. Here beta 1 is 0. But so before I take questions, now just think of the implication of it. If beta 1 is 0, what is it saying? Beta 1 is associated with some feature, some predictor. If that predictor has 0 value, what is it saying about that predictor?
Taking it out of the model.
It's taking it out of the model. It's saying it's irrelevant. So what have you done? You have achieved something that is actually a good news or a bad news, depending upon how you look at it. You have created a model, a simpler model with less features, isn't it? You have created a simpler model with less features, right? And I will sort of stop here because it's been a long intellectual journey, but what it, and it's going to be lunchtime now, but what it means is that Lasso regularization has the ability to eliminate some of the features, right? And the way it works is quite interesting. And here you'll have to take my word at it. What it does is that suppose you have different parameters. So based on the value of the lambda, one of the beta, let's say that beta naught will go, beta 1 will, beta 1, beta 2, beta 0, beta 0. Ultimately, if you make your lambda too big, all of the betas will disappear because they'll all keep shrinking. Now you keep getting to some axis. So what happens is if you choose your lambda here, this particular point of lambda, what will happen? Beta 1 has disappeared and beta 2 has remained. Beta naught has remained in this particular example, right? Let's say beta 3, beta 2. So what will happen? How many betas remain? Beta naught and beta 2. So beta naught or beta 2 remain at A, at cutoff A. Beta 1 gone. On the other hand, if I put the cutoff here at B, if B value of lambda, what happens? How many of them remain? Only beta 2 remains. Beta 2 still has this value, isn't it? So these values are still present. What about beta naught and beta 1?
They drop out.
They drop out, exactly. A beta naught, a beta 1 are dropped off. Right? So what happens is that, and this is the risk with Lasso regularization. Its strength is that it can lead to simpler models. Sometimes predictors or features that don't matter so much, they tend to disappear. Good thing with Lasso. Ridge regularization will make their parameter values small, but it won't set it to 0. But Lasso will cleanly wipe them out. But the risk with Lasso always is it over-regularizes. It may get rid of factors that actually matter, but you over-regularize them out of existence. Are we together? And that is the risk with Lasso. So questions. Now, I know that there were questions waiting.
Why would anybody use Lasso?
Oh, this is a very good question. Why would anyone use Lasso is the question. The answer to that is, a priori, you don't know whether it's a good idea to create a simpler model or it is not. Are we together? Ultimately, it's after building all sorts of models and doing search and looking at the error, right? Testing error, that you ever know what was the right thing to do. Right? And this goes to a heart of something that I'll teach you later on. It has a lovely name, but I won't mention it. In machine learning, there are no perfect answers. You cannot say that use Lasso or don't use Lasso. Always the data rules, data speaks, right? So for certain situations, it works better. For certain situations, it doesn't work so well. And even then, the choice of the hyperparameter rules the day, right? What the lambda is one of the hyperparameters. So now when you look at regularization, you have 3 degrees of 3 hyperparameters that we have encountered. And with that, I'll summarize hyperparameters now let me just call it L star regularization, means L star regular. By star, I mean whatever, 1, 2, 3, 4, whatever. Regularization RA with polynomials. I will just take example of polynomials. It is generalizable to everything else, but I'll just take 1 degree of the polynomial isn't it? 2 lambda strength of the damping or regularization. How much are you regularization? And the third, which norm? Ridge L2, Lasso L1, or you could mix the two, elastic net. You can add both the terms, right? Both of the constraint terms you can add, or something else. You realize that. So when the same thing that you're trying to model with data, but now you notice that life is getting complex. You have to keep on building, training the model with different values of the polynomial, different lambdas, different, do
these norms actually obey linear operations like additive?
There's no, so you can derive what properties it will have literally from the definition of the Minkowski norm. So from this, you can do that. But in general, because of the nth power effect, right, they are not very amiable to linear. They are not linear operators. Okay. They are not linear operators, if that's a question. Right, they're not. Right. So that is that.
Could you explain that the last diagram again, really quickly?
This diagram, right? So
Yeah.
what happens is that when you solve the problem, you will see that as you change the strength of the regularization constant, the optimal betas that you find after machine learning, their value, let's say that at no regularization, the values are huge. This is your beta 1, this is your beta naught, this is your beta 2. These are the values, the absolute values. Then what happens is you can actually check that as you increase the regularization constant at different values of the regularization constant, what are the betas? What are the values of the betas? You know that they're shrinking. They are all shrinking their way to 0. Isn't it? The whole point, that's why they're being dampened down. But they are going towards 0 at different rates, right? But some are going towards 0 slowly, some are going to 0 aggressively. And so your choice of lambda does determine what values you'll have for the betas finally in your model.
So lambda is independent of the norm n, right?
Yes, totally. It is. That is why it's a hyperparameter of the model. You fix your lambda and then the learning will take place. You have to fix your lambda, you have to fix your norm, and you have to fix your degree of the polynomial. And then learn, and then the betas will come out, the parameters will come out.
Okay, thank you.
That is it. That is the interesting thing. You don't learn the hyperparameters using gradient descent. Hyperparameters you have to choose. But whatever hyperparameters you choose, after learning, you'll get the optimal betas for that hyperparameter value.
So Asif, one question is like, so that parameter that the beta naught or beta 1 goes away at the specific value of lambda or greater than equal to a specific value.
That is right. Once it has flattened out, it will remain flattened out. Like for example, once it has hit 0, it will remain 0 for all values greater than that. So for example, look at this point. Let me call this point C. At lambda is equal to C, beta 1 goes to 0. So for all values of lambda greater than C, beta 1 will forever remain 0. It stays flattened out.
Okay.
Right? It disappears. Once gone, it's gone forever. It doesn't come back.
Okay.
Right.
Thank you.
So that
So
is
that's what is causing the feature to drop, right?
Yeah, that's what's causing the feature to drop. Excellent.
So that becomes the limit, so that we can control the features.
Simplifying the model, what happens is that you initially said, let's take a hypothetical example, that if you want to regulate your blood sugar, you need certain amount of exercise, certain amount of age is a factor, then certain amount of, I don't know, food, how many calories you took in is a factor, right? And let's say that there is also a factor that says certain amount, the size of shoes or whatnot is a factor, right? Hopefully not, right? Otherwise we'll all start wearing different size shoes. But let's say, so what will happen is as you play around with it, hopefully you find that some irrelevant factors, they're beginning to drop off. The size of your shoe is beginning to broadly drop off. Right? It may have a small effect. Like for example, children wear small shoes and they tend not to have diabetes, right? But amongst adults, that relationship doesn't quite hold. So, the less relevant factors begins to drop out. Now your model ultimately might end up by saying, okay, for the larger population, broadly, age, calorie intake, and level of calories burnt, exercise, are the 3 determining factors, and all other factors have dropped off. right? And you wanted to say something like that. For example, you don't want, if the data came with size of shoes and color of shirt and all those things, you would hope that the betas associated with those features have dropped off. Right? And with rich, what will happen is they won't exactly vanish. They'll just become tiny, right? They'll become tiny.
Okay.
If I'm understanding this right, in the regularization, like the equations
Yes.
for Lasso, so
Yes.
because we want to minimize the loss, if we increase the lambda hyperparameter, we in turn then have to compensate by minimizing the parameter term.
No, you cannot. During the learning gradient descent process, you can't touch lambda. It's a God-given fact. The learning process doesn't touch lambda. The finding the best lambda is the hyperparameter exercise. You have to do a search, find the best lambda that overall will give you betas that minimize the test error.
Yeah. So what I'm saying is, so you're saying as we are increasing lambda, right? As we are increasing lambda, in order to compensate and to make sure we minimize the loss, we in turn have to dampen the parameter term, the beta term. Because in the equation, it's lambda times the summation of.
Let me do that. Because you're increasing, that is exactly what happens. Because if you increase lambda in the equation, that is a beautiful point you made. Why do the betas decrease? Because if you increase lambda, beta in compensation has to decrease. Otherwise, the loss won't go down.
Yeah.
Right? And so what happens is that your best solution is very sensitive to the lambda. If you take large lambdas, all your betas in the answer will turn out to be small. In other words, they'll be close to the origin. Right? That is the main point.
So, Asif, so actually Lasso is making sense in the way that it is making like model more interpretable by removing some features.
That is true.
So if a feature is derived based on like inputs from domain experts and the original feature gets removed in this process, can that happen?
Yeah, it can. See, remember that ultimately, what is the judge? Who is the judge? The judge is that model using Lasso, using Rage, using different values of lambda, using different, if you're doing polynomial, then of course, different degrees of point. That model, which ultimately yields the lowest test error, isn't it? And so when you do that and you look at that model and happen chance, it turns out to be a Lasso model with a certain lambda. And let's say that that Lasso model with that lambda eliminated two of the features. Then the truth is those features didn't matter. Right? You can go back to the domain experts and you tell them that, guys, I know that you thought this matters, but we found out it doesn't matter. And it happens all the time, guys. All the time it happens that the after data science, you discover a new truth, right? You come to a different picture of reality a posteriori. Right? You say this matters a lot and this doesn't matter so much.
So Asif, how do I know that how long I need to keep trying, whether I go to reach it in Lasso and then something else? So what is the error that I have to look at that gives me that I need to try more?
Test error or the test loss. Find that model which gives you the lowest loss on test data.
But how do you define the lowest? So you take the test 1 and test 2 and test 3.
Yeah. Remember, there's this equation. At the end of the day, you have the data, so you can compute this and find that loss which is lowest. And it is hard because during the gradient descent, lambdas are not learned, hyperparameters are not learned. So you just pick some value of lambda, some value of with choose Rage or Lasso or whatever, some regularization, do it. Then you make a table. See, what will happen is that you will end up with L0, L1. As you do experiments, suppose you do K experiments, you will end up with K losses. From this, go and zero in to that particular loss, which was minimum. What is the minima amongst these losses? Whatever model that loss corresponded to, whichever experiment that loss corresponded to, see what were the hyperparameter values you set, for that particular experiment. And those are the things that you will use, and the answers are the betas that came out of it. The model that came out of it is the model. So it is a very, and we will talk about it. How do you search for the best hyperparameters? There are techniques like grid search, randomized search, etc. I will explain that at a later date. But for today, we want to focus only on regularization and just sort of assume that randomly you go about shooting at guesses. But we'll do better than random guesses. And we'll come to that. We'll come to that of how to systematically find those. It's a broad topic in its own right, and it goes to the heart of one of the hottest things these days. It's called automated machine learning. How can a machine learning learn the hyperparameters itself? And this gets very interesting. How can, for example, a deep neural network re-architect its own shape in such a way that it solves that problem best? Right? It's a very vast and beautiful subject, but we will take baby steps at some point.
Asif,
Go ahead.
so if you scroll down, you have L1 plus L2 together. Can you explain a bit of effect of that?
The elastic net, for example, it basically says, what if we took the loss function to be the sum squared error, the yi minus yi hat term. This is a given, right? Sum squared error we are not touching. But you have lambda 1 for absolute value of beta plus lambda 2 for the square values of the beta, sum of square values of beta. So what did you do? You added both the terms, both the regularization terms, and you're saying now you have two hyperparameters in the two suppression parameters in this model, lambda 1 and lambda 2 both. One comes from Rich or one comes from Lasso, and let's add both and minimize this thing, right? So people do all these combinations and they try it out. One of the frustrating things in machine learning that people, beginners always ask is, God, surely there has to be a way, there has to be a correct way to go about it. And the answer to that is no. Algorithms, you don't know a priori which algorithm will work best or which hyperparameter combinations will work best. It is the data that picks one, and you don't know which one it will pick when you try to model with it. So there is a name for that beautiful result. It is called the no free lunch theorem, and it is one of the most profound results in the theory of human knowledge, actually. It has far-reaching consequences. We'll talk about that at some point. Later date, it will come, actually, in this workshop itself, it will come. No free lunch is a big topic, right? But today, it's time for lunch.
One quick question. So when you talked about the Minkowski norms,
Yeah.
that was a generalized concept.
Yes.
It could be different norms.
Yes.
But when we explored how Minkowski norms have been used in regression, we stopped with L1 and L2.
L1, L2, mixtures of them are, these are by far the most common, but people do use other norms. They do use. Right. All right, folks. So it is past 1, it's 10 past 1. I have a request for you. Have your lunch and then give your 90 minutes, usual 90 minutes for lunch. But I noticed that most of you have not taken all the quizzes. So I want you to give half an hour right after lunch. I won't start till I look into the course portal and I see that the majority of you have taken your quizzes, right? So you must take your quiz before I start.